Okay, this is makeup for Monday's lecture. I'm just kind of recording this by myself in my office. I'm going to stick this on YouTube so that people who are interested can watch it, but it's highly unlikely that this will be on the exam. I just want to make sure that everybody gets their money's worth for the course, and there have been a couple students in this class in the past who've used some of the material from this lecture, so it's out there. But as I said, if I doubt you'll be tested on it, and if you don't want to watch this, you'll probably just be just fine because it was my fault for not showing up for class anyway. So, without further ado, today, it's kind of funny how I lap into my usual lecturing strategy even when I'm just talking to myself in my office. I'll just, for the sake of argument, I'll say today we're discussing survival data, which typically means the amount of time when you want to see what factors are associated with the amount of time before a particular event occurs. Typically, you're measuring the amount of time that something stays alive or the time until something fails. That's why we use the term survival data. One of the most common examples is in cancer studies. You want to see what risk factors are associated with the survival of the patient. Or if you were studying infectious disease, you could inject a mouse with a virus and see how long it lives, or it doesn't necessarily even need to be actual time to death. If you were doing product manufacturing and you wanted to measure variables associated with the amount of time that your light bulbs last, you could use survival analysis for that. I'm working on a big study of temporomandibular disorder right now. It's a prospective study where people were TMD free at the beginning of the study, and we followed them for several years to see who developed the condition. We used survival analysis for that, with the event being when somebody developed TMD. And we need some specialized methods to deal with this type of data for reasons that I'll discuss shortly. The big issue that makes analysis survival data more challenging is censoring, which means that basically at the end of your study, a lot of people will still be alive. For example, you're doing a cancer study, and at the end of the study, the patient hasn't died yet. We don't know if that means that they're going to die 2 months later, or if their cancer's cured and they're never going to get the disease. Or in some cases, a patient may drop out of the study. We may lose contact with them. In either of these cases, this is called censoring, which means that if somebody dropped out of the study after 6 months, for example, we know they survived at least 6 months, but we don't know their exact survival time. So all we know is that as of 6 months into the study, they were still alive. And oftentimes, if you have a small amount of missing data when you do statistical analysis, you can just exclude the missing data from your data set when you do the analysis, but that's usually a bad idea in the survival situation. That in survival analysis will usually result in severe bias. For example, if you know that a large segment of your cancer patients survived at least 5 years, maybe these were the patients who were cured or the patients who had good treatment outcomes. If you exclude all of those, then the only remaining patients in your study are those with the poor outcomes, and you end up with severely biased sample and incorrect conclusions. So simply excluding the observations with missing data isn't a good option. The best plan is to develop methods that can take the censored data into account. So there's several different questions that we may want to try to answer using survival data. I'll go through these one by one. The first issue that we may want to consider is just estimating the survival function. In other words, just estimating the distribution of the survival times for the patients. If you have a given type of cancer, what's the probability that you'll survive at least 5 years? What's the probability that you'll survive at least 2 years, for instance? Trying to estimate that. And to do this, first we need to set up some notation. First of all, we'll say let t be the time of death for a given experimental unit, a given cancer patient, or whatever. We define a survival function s of t to be the probability that you survive till at least time t. So in the cancer example, if it were 5 years, s of 5 would be the probability that you survive 5 years or longer. And so how do you estimate the survival function? Well, the simplest way to do it is you just take the number of patients who survived at least 5 years, divide by the total number of patients. Well, unfortunately, it's a little more complicated than that if they're censored observations. What about the people who stayed in the study for 3 years and then dropped out? Would they have survived for 5 years? Who knows? But we can't simply uh, but we can't simply take the number of people who survived for 5 years divided by the total, because some of the people who were censored before 5 years may have survived that long, so we have to use a slightly more complicated approach. So to do this, we establish some notation. I apologize for all the notation here. This really isn't as complicated as it looks, and if you ever need to do this, R will do it for you. But we can use the following notation. Say that we observe the deaths of n subjects, and we'll say these occurred at times t1, t2, up to tn, that are ordered from the smallest to largest. And for each t, we define di to be the number of deaths that have occurred up to that time point, and ni to be the number at risk who are not dead or censored at that particular time point. And so let's take a simple example. Say we have 10 people in our study. We have one person who dies at time 3, another person who's censored at time 9, and a third person dies at time 11. Then we only have to define T2s. T1 is 3, which is the time the first patient died, and T2 is 11, which is the time that the third subject dies. So at T1, when the first person died, we have 10 people in the study, and there's 10 people at risk, meaning people who haven't died and aren't censored, people who are at risk of dying, and there is only one person who's actually died. And then when the second event occurred, there's only 8 people at risk at T2 equals 11, because one person's died and one person's dropped out of the study, and the second death occurred at time T2, so D2 equals 2 at that particular time point. And so the most commonly used, in fact in practice virtually the only used estimate of the survival function is what's called the Kaplan-Meier estimate of the survival function, which just means to estimate the probability of surviving up to at least time t, you go to every single time point before time t where there was at least one death, and then at that time you take the number who are still alive at that time divided by the number who are at risk at that particular time. So I think I give an example of this on the next slide. Oh, apparently I don't. I should add an example of this to next year's slides to try to make this a little bit more intuitive, but like I say, R will do this for us. It doesn't matter that much if the whether you understand the details, but if you go to the simple example from a couple slides back, well, I'll just jump one back to it, that say you want to find the probability that somebody survives at least 5 time units. Well, at time 3, there were 10 people at risk and 1 person who had died at that point. So at least 90% of the people survived that long. So in this case, S of 5 would be 0.9 because there's a 90% probability of surviving that long based on the date. And let's say we want to find the probability of surviving up till time 12. Well, in that case, it would be 0.9 of surviving at least up to time 3. But then we have to consider the probability of surviving up to time 11. In that case, it would be 8 people at risk at time 11, 2 who have already died, so 8 minus 2 divided by 8, that's 0.75, so the probability of surviving till at least time 12 would be 0.9 times 0.75. If you didn't follow that, like I said, R will calculate this easily, so it doesn't matter that much. Oh, an example of this using a data set that's built into R is acute myeloid leukemia. In this case, there's 23 patients with acute myeloid leukemia or AML. Each person was followed until they either died or until they dropped out of the study. So we have 2 variables here. One is the time, which is the time until either death or censoring occurred, and the second is the status, which by convention is equal to 1 if the patient died or 0 if the patient is lost to follow-up. That is, if they were censored. Our objective here is to estimate the survival function. Oh, to estimate the survival function in R, there's 2 commands you need to know. The surv function just takes 2 vectors and converts it to a survival object, and survfit is used to estimate the survival function for a given survival object. So in this case, at leukemia data, if you do summary for the survfit command, you see that at time 5, which is where the first event occurred, there were 23 people at risk and 2 events, so the probability of surviving at least 5 months is 91% approximately. Likewise, the probability of surviving 8 months is about 82.6%, 9 months 78.3%, and so on down the line. And hopefully this is reasonably self-explanatory. And you'll also notice that survfit takes a formula object where it says a survival object twiddle 1. That's just saying there's no covariate that we assume affects survival. We just want to calculate survival for the full cohort. I'll show you how you can estimate survival when there's a covariate here in a second. So, in general, if you say surv y and IC, that will create a survival time object in R. Recall, survival times in general consist of like the time that they were followed and then an event indicator, which is 1 if there was an event or a death, or 0 if they were censored. And you give it 2 vectors y and IC and say surv of y and IC. And then if you say survfit of a survival object twiddle 1, that'll calculate a Kaplan-Meier estimate of the survival function. Like I said, this assumes there are no predictors. If there are predictors, then we have to use slightly different notation that I'll describe shortly. So to plot the survival curve in R, you just basically plot the result of a survfit object. See, we fit a survfit object just like we did before, and then we pass it to the plot function. You can give it an x-axis label and a header label, just like normal. And yeah, this gives you a Kaplan-Meier plot. And I guess I should have mentioned that if you plot the probability of survival versus the survival time for a data set like this, that's known as a Kaplan-Meier plot. So if you look at this plot, the probability of surviving, it's hard to read on with the large x-axis scale, it looks like there's only about a 0.1 or slightly less probability of surviving to 50 months. Before that, it's difficult to read. And basically, on this graph, the solid line is the estimate of the survival curve. The two dotted lines are the upper and lower 95% confidence bounds. You'll also notice that a couple spots on the line are marked with a little plus sign. Those are the observations that were censored. So it looks like around maybe 20 months or so, someone dropped out of the study, and then a second one dropped out about 30 or 40 months. And then there was one person who survived like 150 plus months who was presumably cured of their AML. And yeah, I guess I already said most of this. The dotted lines represent the upper and lower 95% confidence bounds, and a plus mark on the graph indicates a censored observation. So that's how you estimate the probability of surviving to a given time. Let's say that we have two different groups and we want to know if there's differences in the survival times of the two groups. And you can obviously just calculate the Kaplan-Meier plot separately for each group, but you might also wonder, well, is there a statistically significant difference between the two groups? Is there a predictor that has an effect on the survival time? In this particular AML example, some subset of the patients received an extended dose of chemotherapy, and we may want to know, if you get the extended chemotherapy, does that increase your expected survival time, or is it not really accomplishing anything? Oh, in this case, to answer this question, we can use a slight modification of the survfit command. Rather than saying survfit time status twiddle1, we say twiddlex, which in this data set, which is built into R, by the way, it's built into the survival package. I should have mentioned that sooner. I guess that's another issue that I forgot to mention, that the survival functions are not loaded in R by default. You'll have to do a library survival command to get it to load the various survival functions. And so here we say summary survfit time status twiddlex, where x is a two-level factor that's either maintained, they got the extra long chemotherapy dose, or it's non-maintained. So we can see that, so for instance, this tells us if you got the extended dose of chemotherapy, your probability of surviving to time 13 is about 0.8, versus the probability of surviving to time 12 is about 0.58 if you didn't get the chemotherapy. So it does look like the extended chemotherapy might be helping a little bit, but there's still a question as to whether it's statistically significant. And in general, if you say survfit, a surv object twiddlex, that'll calculate a Kaplan-Meier estimate of the survival function for each possible value of x, where x should be a factor with two or more levels. And you can also plot both Kaplan-Meier curves together in R just by plotting a survfit object, as you see here. In this case, it looks like this. You'll notice in this case there's no confidence intervals. You just see the two plots. They don't include confidence intervals when you do multiple Kaplan-Meier plots on one graph, because the worry is the graph will get too busy, basically. And again, it looks like, and it's possible to label these graphs. I didn't, just because I didn't want to confuse you, but you can just take my word for it. The top group got the extended chemotherapy and the bottom group didn't. So consistently, it looks like at any given time the probability of survival is better with the extended chemotherapy group. We're not seeing enormous differences here. And so that's nice. We can do we can plot the Kaplan-Meier curve separately for each level of the factor, but what if we want to test the null hypothesis that the survival function is the same for each group? Or more specifically, let's say we want to test the null hypothesis that the extended dose of chemotherapy has no effect on the survival of AML patients. Turns out there's a test that you can do for this that's called the log rank test. And this test statistic is complicated, but R will calculate it for us, so I won't bore you with the details of how it's calculated. The command to do it in R is called survdiff. Syntax very similar to survfit, but rather than calculating the Kaplan-Meier curves, it just tests the null hypothesis of no difference between the two groups. Basically, all we care about here is the p-value down at the bottom, which is 0.065. So if you use the conventional p less than 0.05 cutoff for statistical significance, then we would conclude that there's not a statistically significant difference between the two groups, but it is worth noting the sample size here was not large, so our power wasn't great, and it's still borderline significant. So to me, I wouldn't necessarily conclude that there's no difference between the two groups, but rather I'd conclude that maybe we don't have enough power to detect the difference between the two, and that maybe we should recruit some more patients to this study to see if we can make it over the magic 0.05 threshold that will make it so that journals are willing to publish our paper. And in general, if you say survdiff, a surv object twiddlex, that'll do a log rank test, just same notation for survfit. X needs to be a factor with 2 or more levels. It'll do a log rank test, test the null hypothesis. The survival function doesn't differ between the various groups. And the final thing that we may want to consider in survival analysis is the analog of regression. Say that we want to do a more complicated model, that rather than just saying extended chemotherapy versus no extended chemotherapy, we have a series of possible risk factors, and we want to include all of those in the model. Say, for example, you do a series of tests on a cancer patient to evaluate how severe their cancer is, and you want to try to make a prognosis for the patient. This is similar to ordinary linear regression, except this time the response variable is a survival time rather than a continuous outcome, so we have to use a specialized type of regression for this. And the way this is normally done, in fact practically the only way this is ever done in the literature, is to use something that's called a Cox proportional hazards model, which uses something which tries to estimate something called the hazard rate, which the hazard rate is defined to be the death rate at a given time t, given that the subject survives to time t or later. It turns out, for various reasons, it's usually much easier to predict the hazard rate than the actual survival time. So, given a set of predictor variables, we try to say how much more likely is a person with this set of predictor variables to die at any given point in time compared to some baseline. And this is known as a Cox proportional hazards model. And so an example of this using another data set that's built into R is the lung cancer data set. There were a total of 228 patients in the study with advanced lung cancer, and each patient's survival time was recorded along with several risk factors that are known to affect the survival times of cancer patients, or at least were believed to affect the survival times of cancer patients. We want to know what effect these risk factors have on a patient's risk of dying. So the function to do this in R is called Cox pH, and it's a very similar notation to LM or the other regression modeling techniques that we've discussed in this class. The difference is that Cox pH, the outcome variable, instead of just being a continuous number, it'll be a survival time. So here we say Cox pH Surv time status. Time is the time till either an event or they drop out the study. Status is 1 if it's an event, and 0 if it's censored as usual. And then the predictor variables in the usual notation. So age, sex, ECOG score, Karnofsky score, and weight loss. And the output here, for the most part, can be interpreted the same way as in a regression output. Well, at least the z-values on the side. Those z-values are just p-values for testing the null hypothesis that a particular regression coefficient is equal to 0. So, for example, for age, Karnofsky score, and weight loss, we fail to reject the null hypothesis that these coefficients are equal to 0, but there is good evidence that gender and ECOG score are significantly different from 0. And down at the bottom, there's 3 overall tests that are comparable to the F test from linear regression. Test the null hypothesis that all the variables are equal to 0 simultaneously. Which one do you use? Most of the time it doesn't matter. I'm not sure why they report all 3, because usually there's very little difference, but you can just pick your favorite and report it. The one thing that's not totally intuitive is how you interpret these coefficients. They're sort of like logistic regression coefficients in that the coefficients are calculated on the log scale, so e to the coefficient is the quantity that you're most interested in. For example, if we take e to the coefficient for gender, it's 0.5318. What that tells us is that if you're female, your risk of dying at any given time point is approximately half what it would be if you were male. Likewise, if you're male, that's the exp of minus coefficient, your risk of dying is about 1.88 times as great. An ECOG score is a continuous number from 0 to 5, I believe, where I forget how it's defined exactly. I think 0 is you're in good health and 5 is you're dead. For every 1 unit increase in your ECOG score, your risk of dying approximately doubles. Note this is on an exponential scale, so if your ECOG goes from 0 to 2, your chance of dying are around 4. If it goes from 0 to 3, it's on the order of 8. So obviously that's quite strongly associated with the probability of survival. So, in general, if you say Cox pH, survival object, y, IC, twiddle x, that'll fit a Cox proportional hazards model to predict a survival time based on a covariate or series of covariates. The code that you enter into R is exactly the same as you do for ordinary linear regression with the LM command. And to interpret the output as, I guess I basically described this before, when age increases by 1 year, the risk of dying increases by 1.015. And the risk of dying for women is about 0.53 times the risk of dying for men. Blah, blah, blah. So the raw coefficients are hard to interpret. You should focus on e to the coefficients as I described earlier. The 3 tests at the bottom, I guess I went over this briefly as well. They test the null hypothesis that all of the coefficients are equal to 0. It's just like the F test for ordinary linear regression. And in virtually every example that I've seen, all 3 tests give nearly identical results. You can just choose your favorite to report in the paper. Oh, there's certain... Just like ordinary linear regression, the Cox model makes certain assumptions, and I won't go into the details of these assumptions because it's confusing. This is pretty advanced material for an intro course. in the first place. I mean, one of the big assumptions of the Cox model is that the hazard rate, the baseline hazard rate, really does not vary over time. There's various commands in R to test that, but they're beyond the scope of this class. Sometimes journals will ask you to test this assumption. If they ask you to do it, then your best bet is shoot me an email or send some other statistician an email and ask them to help you with this. But I will note in passing that multicollinearity can cause the same problems that you get with ordinary least squares. If you have a bunch of correlated predictors variables in a Cox proportional hazards model, you'll get into trouble. And the same types of solutions can be used for survival analysis. You can do principal components regression, or if you really must, there's stepwise regression, I suppose. You can also do penalized regression. The GLMNet package in R will handle survival data just fine, but I'm not going to ask you to do it in this class. Well, I might potentially put a bonus question about this on the final, but I kind of doubt it. So, things to remember for today's lecture is that survival data, when you have censored observations, require special analytic methods. If you want to estimate how long experimental units will survive, you can use a Kaplan-Meier estimator. If you want to compare the survival functions of a couple groups, then there's a log rank test. You can also predict the hazard rate for a given set of predictors using a Cox proportional hazards model. And here's a list of R commands that I discussed today. And I guess since I'm just giving this lecture to myself in my office, there's no need to belabor the point. So thank you for listening.